We have been talking about how we would find these areas over and under estimates. And we have said that the more rectangles we have, the more accurate it would be, right? So the true area would be as the number of rectangles is going to infinity. So we're going to be doing the limits as these things approach infinity today. First, I wanted to look at this example. And you should have the notes handout that I had printed for you. This should be the next. I think I skipped one, but it's the next one. All right, I want you to look first at the numerator here. 1 plus 2 plus 3 plus 4, all the way up to n. Could I write that as a sum? Okay, that's the sum as I'm adding up from 1 to n, and I'm just adding up what? N, or I'm using I as my number. So it's just I, 1. So that would be our summation notation that we were using last Thursday. Then Friday, I gave you a formula for how you add up powers of I, right? We did I squared, and I cubed. The I formula was n times n plus 1 over 2. Okay, so this top, by using my summation formulas, adds up to n times n plus 1 over 2. And this whole thing is divided by n squared. We know if we want to evaluate a limit, any simplifying we can do would help us. So this is like n squared over 1. To divide fractions, we flip and multiply. So I have n times n plus 1 over 2 times 1 over n squared. So we can cancel an n. So I have n plus 1 over 2n. I could split that up. If I did n over 2n, what would that simplify to? Plus 1 over 2n. If n's going to infinity, 1 over 2n is turning into 0, so I get 1/2 plus 0, which is 1/2. Right, so I think on your handout from Friday, that was what the type of question for the last one. You had to use your summation formulas to figure out how to add up the top, and then you could simplify and do the limit. All right, any questions on that? I want to go to we're going to do the next few examples before we work on the homework. So if I want the true area under a curve, we have to have a starting and a stopping point. So this curve has a definite length, n. And then we're going to divide it into rectangles. And the number of rectangles needs to go to infinity. So if I wanted the true area under the curve, f of x equals x squared. If you remember, like last Thursday-ish, we did x squared, we approximated the area with, I think, 5 rectangles and then maybe 10 rectangles, so we had a couple of approximations for this. Let's figure out what it really is. So to do this, you need to first calculate your change in x. And my interval ends at 3, it starts at 0. So it's just the ending minus the beginning, and I'm dividing that into n rectangles. So my change in x is 3 over n. That's the width. The total length of my interval, 3 divided by my n rectangle. Then I am going to write what's called x sub I. It's basically a formula for each x value that we plug in. Right? We knew when we did these, the width was my change in x, and I was plugging in a different x every time. what's the starting point here? 0. So it's always your starting point plus your change in x times I, okay, because you'll add the 3 over n the first time, and then the second time, and then the third time. So this is how we'll find it every time. So for us, this turns out pretty nice. It's just 3 over n I. That would give us our x value at any given point. So if I'm going to do the sum, I need to add up from 1 to n the area of these rectangles. The area is length times width. They all have a width of 3 over n. And to get the height of those rectangles, you are going to plug the x into the equation. It would be 3 over n I squared. Length times width. Have I lost my...
The change in x, that's our width.
Mm-hmm.
Okay.
And the height of those rectangles is what you get when you take the given x and plug it into the
Oh,
equation.
so when you say rectangles, that's the, like, that's what we're putting inside the curve. Okay, that makes, I was just thinking like, we're finding rectangles.
Oh, no, remember
I was
like
kinda lost, I was like, okay.
when we were drawing 5 rectangles under the curve and adding up their areas. And then we did it with 10 and added it up. All right. So if I simplify this, 3 squared is 9, times 3 would be 27. N squared times n would be n cubed. Bless you. And we have 9 squared. Okay, we're adding up i's. 27 over n cubed, that doesn't have an I in it. That's just like a coefficient. Times, then I'm adding up I squared. What's the I squared formula?
N times n plus 1 is 2n plus 1 over 6.
Remember that's from Friday. We did I squared, and I cubed. All right. Now, this is just a matter of working it out. All right, so that's, my summation is gone because I did the sum formula. We could cancel one of these ends. And if you wanted, you could reduce 27 and 6. And now we're just going to multiply things out. So I have 9. If I FOIL that, so then can I distribute the 9 and divide by my 2n squared at the same time? So 18n squared divided by 2n squared would just be 9. 27n divided by 2n squared would be 27 over 2n. 9 over 2n squared. All right, so what we just found is a formula for those areas under the rectangle. So now if I said 5 rectangles, you could plug a 5 in and figure out what it would add up to. If I said 10 rectangles, you could plug in 10. But if I want the true area, what needs to happen to my number of rectangles?
As many as you can.
Which one's going to be more accurate, 5 or 10? 10. All right, what about 10 or 100? What about 100 or 1,000? So what's happening to my number of rectangles? It's getting bigger and bigger. So what we need to do is find the limit as n goes to infinity. And because we've already done all the legwork of simplifying this, it's pretty easy. We know a number over infinity goes to 0, so we just have 9 plus 0 plus 0, which is 9. So the actual area under our curve is 9. If you look back, the very first example, we did this, and with 5 rectangles, we said it's somewhere between 6.48 and 11.88. With 10 rectangles, we said it's between 7.695 and 10.395. So we were narrowing it down. Now we know the real answer. All right. Let's try setting up another one of those. So I want the area under the curve, 100 minus 3x squared, from x equals 1 to x equals 5. The very first thing you have to do is find our change in x and our formula for x sub I. Change in x is always your ending minus your beginning divided by n. If I'm starting at 1 and ending at 5, this is 4 units long, dividing it into n rectangles. So my change in x each time will go up by 4 over n. X sub I. Where is this one starting? Not at 0 this time. 1. So it'll have to be 1 plus, then we add our multiples of 4 over n to that. So it's whatever number we start at, which a lot of the times is 0, but this time it wasn't, plus our multiples of x. Now we have to do our sum. Okay, we have to add these things up. So we're adding up from 1 to n. The area of a rectangle, length times width. So all of these have a width of 4 over n. All right, to get the height, we have to plug our x sub I into this formula. So it would be 100 minus 3 times, I am just replacing my x with that x sub I. Squared. I lost. Now is probably the longest part of the problem, but it's just algebra. We're just going to multiply this stuff out and simplify. So I will sum from 1 to n over n. All right. So if I were just to square that inside, we'd have to FOIL. So it'd be 1. Over n I, 16 over n squared I squared. Would it be okay with you guys if I distributed my 4 over n into this negative 3 on this stuff? So 100 times 4 over n will give me 400 over n. Okay, if I distribute my negative 3 and my 4 over n, so that will give me a negative 12 over n. This would be negative 24 over n I times 4 over n, so negative 20. Over n squared I. Okay, negative 3 times 16, so negative 48. And then we also have to multiply by our 4 over n, so I get 192. N times n squared would be n cubed. it just multiplied out that whole thing. Now we have to do the sum. So that's what we are working on Friday. We are adding up i's. Okay, so if I'm adding it from 1 to n, you could combine these. 400 over n minus 12 over n, these are like terms, right? So that would give me 388 over n. When I add those up, do they have an I in them? So that means every time you're just adding it up. Do you remember from Friday, how do we add up a constant? I'm adding that up the first time, the second time, the third time, the fourth time, all the way to the nth time. So we just multiply that by n. Okay, when I add up I, what's the formula for I? I squared. What is the formula for I squared? No, it's just back to algebra. So the amount of calculus is really like the setting it up and the summation formulas. Otherwise, these problems are a lot of algebra, multiplying and simplifying things. So I would get a 388. I can cancel one of these n's. 96 divided by 2 will give me 48. Divided by 6 is 32. Cancel that in. So if I FOIL and distribute, distribute the negative and divide by n. I get 388 minus 48 is 48 over n. Here, distribute the negative, divide by n squared. So minus 64 minus 96 over n minus 32 over n squared. So that's what all the work was, to get this simplified version. And then, what do we have to do with that? The limit as n approaches infinity. Which, if you've done all the work to clean it up, this limit is now really easy to calculate. Anywhere with an n on the bottom turns into 0, so I get 388 minus 48 minus 64. Which gives me 276. Are similar. So you'll notice question number 5 says the speed of a runner increases steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table. Find the lower and upper estimates. So it's a finite amount of time. We only measured her speed every half a second, so we can't do the limit as n goes to infinity here. This is more straightforward, kind of a review of what we were doing on Thursday with our lower and upper. And when I look at these, what's the width of my interval every time? The change in x. And that was a half second. All right. So for my lower limit, if we look at this, the speed steadily increased, right? So the lower limit would be starting with the leftmost point. And you would have to end before the last one. Does that make sense? So between 0 and 0.5. Okay, at 0 seconds her speed was 0. At half a second her speed was 6.2. We know she didn't run 0 the whole time, she didn't run 6.2 the whole time, right? But it would be estimating the speed using one of those two numbers. So for the lower estimate, I would estimate her first speed to be 0. Basically, we're using the speed at the start of that interval. So for between a half and 1 second, my speed would be 6.2. Between 1 and 1.5 seconds, we would use between 1.5 and 2 seconds, we use between 2 and 2.5 seconds, and between 2.5 and 3 seconds. So the difference is we're using the leftmost point, so that means we don't use the final speed, the 20.2. All right, and so then if I add these up, we get our 34.7. Okay, we are trying to find the distance she traveled. We basically took her speed times the number of seconds, so that is distance. Rate times time is distance. So the lower estimate would be saying she traveled 34.7 feet. All right, the upper estimate, the width is still the same. We're using a half second, but we are using her higher speed in each interval. So between 0 and 0.5 seconds, what speed would we use? Between 0.5 and 1? Between 1 and 1.5? Between 1.5 and 2? Between 2 and 2.5? Between 2.5 and 3? Notice the only difference between these is the first and the last. Unless we give us 4.8 feet. So question 4 is kind of the same. We're just using upper and lower estimates for those time intervals. So now you have some time to work. I want you to make sure you finish that last question on Friday's handout. We're going to grade that one at the end of class. And then you can work on this handout.